Note here on steering in a following current. This is a phenomenon fairly well known to mariners, that if you're in a relatively slow boat and you're in relatively strong current, you have a very poor steerage in a following current, which is important to keep in mind when going through a pass. Say, you say, I'm going to go through this pass with in the right direction with the strong current flowing. Well, you still have to be very careful about that. And likewise, there's some rules here which I'll mention in a moment. But here's the background of this. About 4 years ago, the Ever Given got sideways in the Suez Canal and blocked it. It was quite a major event. And just a few days after that, we did an analysis of it, and nothing was known. Nothing was known at all. But we could go through all the various resources that we teach here all the time, and we could figure out a lot of things, like what the wind was, what the current was, and so forth. And one of the things that we feel at the time contributed to this was the notable following current that affected the steerage of the boat. And and then we had a lot of other things that we had to sort of piece together. Now, it turns out, and we said, well, we'll just wait and see till the Suez Canal Authority makes their official announcement, and then we'll know what really happened. Well, they never did make an announcement. They made a settlement. A year went by or something or other, and then they made a settlement with the shipping company, and as a result of the settlement was, don't say anything about anything, and they never did. However, about another year after that, the captain of the ship that was right behind him made a video. And his video then went ahead and basically confirmed all the things we had made in those earlier videos. I'm going to stop that plug for that work. But it's an interesting work that we did this 4 years ago. Now, it's a very short video. Then following that video, there's 3 backup videos that show the various elements that contributed to that problem, and one of them was the following current. And in that, we presented this picture here. It's just this vector diagram, and this shows a case of a boat going, a ship going 8 knots forward like this in no current. And then here it turns left 30 degrees. And what happens with no current, you turn left 30 degrees, you go left 30 degrees. But suppose there is a current here, you got 3 knots behind you, following current. So then you're going 8 knots in the water, but with your current, you're actually your speed over the ground is 11 knots. But when you turn, you indeed turn. You just read it right off your compass. You turn 30 degrees relative to the water. But the current is still flowing this way. So when your boat's going this way and the current's pushing you this way, so you end up you don't get quite the full turn that you thought you were going to get. And you don't know that when you're in the water, but you do know that if you're turning to avoid a rock or something that's sticking up, because you're going to turn and you're not going to get the turn. Your heading of the boat, it's going to be headed way to the left of the rock, but you're still going to go in, maybe hit the rock, so forth. So this is something that's important to understand, and so we presented it that way in there. Also, we made a note of the Rule 19 of the navigation rules. Downbound vessel in a following current has a right of way over the upbound vessel, and that's because of this very effect. Notice when you're going into the current and you turn, your turn gets enhanced by that head current. So anyway, this was what we presented there. And then we had just yesterday, or actually day before yesterday now, somebody called in or wrote in and said, well, isn't there a way to make a formula for what's going on here, or a way to generalize this? And that seemed to be a good idea. So we stopped and did a little work on that. And that's what I want to present here. And basically, the text outline is in this blog post, which I'll put a link to. But I'm using it now just as an outline to go through here. So here's the math, or not the math, but the geometry we're doing. And the example shown here is 6 knots going this way with a 3-knot following current. So your SOG, speed over ground, 9 knots. Then this boat turns, 40 degrees. So he turns 40 degrees this way. So here he has, in fact, turned 40 degrees. That's what we call angle alpha, how much you turn. and he's going 6 knots through the water like that. But now, if I'm going for every hour that I go 6 miles this way, the current's taking me 3 miles this way. So my course made good is this line along here, course over the ground. Or technically it should be course made good, but anyway, it doesn't matter. That's the course you make good like that. And then that will increase your speed a little bit because you have an addition to it. So that, and we call this angle beta in here, is how much turn you lose. How much turn, I turned 40. In this case, I turned from 270, I turned 40, I turned to 230, and actually was making good on my GPS. I say I'm only making good 243. So I turned 40 and I lost 13. So that's what we just do. And then this is not particularly interesting here unless you care about the math and algebra, trigonometry and so forth. But here's just the equation about how you solve this to get the answer. And here's the answer for the angle that you lose, the amount of turn that you lose, based on R, the ratio of the current to your boat speed. This is the knot meter speed, and that's the current speed. And then how much you turn. So it's sort of exactly what we want, but it's not something you would memorize very well or so forth. But we can make a graph. We can make a graph like this. And you see here, if we have... let's see, I'm going to do an example, but let's just, here's an example here, 0.4. R is 0.4, that's the blue line. And it says a turn of 35 degrees, you lose 10. You see something like that. And I'm going to do an example now where I'm going 6 knots in 3, I want 0.6. I want R equals 0.6. So I'm going to imagine a case of a boat of 6 knots in 3.6 knots of current. So that's either, going through a pass where the current could be that strong easily, many places, at least here in the Northwest, many places they have large passes. You go through currents 3.6 knots. Or you could be in the Gulf Stream or something like that where that's a current. So, and then we're a low-powered boat. We're only going 6. And so if you do let's just see this one I just did. 35. No, R is 0.4. And then there's a table here. So here's a graph and here's a table, which is just this equation plotted as a graph and made into a table. And what's this? 0.4. And then the turn is 35. Okay, so that's in between these two. So I don't get the exact amount. But anyway, 30, 35. You could make this table bigger. Finer steps. Okay, so let's, and then here is a formula. Here is just, this table is created with this formula, which is just an Excel expression of this formula here. And then I just put in here the speed over ground. In other words, that's how much faster you're going when you turn like that. That's the speed over ground here. That if you're playing with this in in a Excel or something, here's a formula for that. BA is equal to BA is SOG, right? BA is SOG and AC is the current. BC. Do I have something labeled wrong here, maybe? Well, anyway, this is supposed, BA is SOG and S is the speed. I'll double check that that's right. I assume it is. Okay, so that's what we've developed to answer the question to the person who wrote in. A little bit probably, and he did acknowledge that's a rather more answer than he expected. But anyway, there you go. That's that. Now let's just do an example about how you really work with this or do it. Here is, for example, the case I just mentioned, and we're using QTVLM, which has one of its very nice features is a simulation mode, and a simulation mode where I can also turn on currents. I can go up here to this and say corrections, and then you see I can force a current over the whole page of 3.6 knots flowing north. Okay, so I did that. You can also force the wind, or you can load real wind from grid files or something. So now I have a vessel sitting here, headed north, and then this is a prediction. This is the heading line, and then you don't... I'm going the same... I've got a COG predictor on here, but I'm going the same direction as I'm not going at all, in fact, right now. So, but you'll see in a minute. Let me turn this on. Let's see how to do that. Okay, a boat, navigation simulation mode. Oh, I am going. Oh, why wasn't the, hang on just a minute. Boat. I must have turned it off. Simulation mode. Oh, I see. I'm in the simulation mode, but I don't have any speed. I'm not going anywhere, right? I don't have any speed turned on. So I can, here's the current though. This, as you study the program, you'll see it has a lot of neat little displays. This shows the current 3.6 going that way. So if I click this, then I can go over here and turn the engine on to 6 knots. Okay, so now I've got the engine on at 6 knots, and yeah. And so now when I read the meters, what do we've got? We've got what makes sense. I've got this is the speedometer reading 6 knots. This is my, quote, GPS reading 9.6 because it's got 3.6 behind me. And my heading, course through the water, that's a heading, true heading, and the cog they're both 0. And what this dot is just set up now to say, where will this boat be in 6 minutes? If everything stays the same, where will this boat be in 6 minutes is right here. And then I've got a heading line that's a half a mile long right here. But we don't see anything. Now what I'm going to do is turn 55 degrees to the left. So let me do that. I can just go over here. Now I'm starting to turn, and then this is where I shut it off. Now wait a minute, let me figure 55 degrees. I want to go to, I guess, 305. So let me keep going here. Whoop, I overshot. So I'll go back a bit. 304, 305. Okay, so now you see what's going on. Now my boat is headed. This is the heading line. That's a half. You can set how long you want this heading line to be. I made the heading line half a mile. That changes in the ocean or in the, in the bay or whatever. And this is where the boat will be in 6 minutes. But you see what's going on. This track here, this track is going to go up this way because this boat is actually now moving. You see, this boat is moving that direction. But and so you see, so what did I lose in the turn? I turned to 305 and I only got to 325. So I lost 20 degrees. But you see, now they can play with this forever in a program like this. So let me go back. Let's see. Let me just see here. The graph. Okay, R is 0.6. 0.6 is green. There's green. And I turned alpha 55 right here, 55. And so I come up here to green, and I lost 20 degrees. Okay, so that's how the table works, and that's our short note on steering and following current.